all families of the core functions or the basic functions can be modified to make them much more versatile and much more closely related to functions we find in applications. That's an important ingredient in this calculus course. The most simple way to modify the core functions like exponentials and powers of x is to transform them somehow. So let's consider the classic simple parabola y equals x squared, and we'll plot it over the interval -4 to 4. So of course we've got our 4 points here, oops, starting at 1 going to 4. That's our x-axis, there's our y, and we have a couple of ground points here. Let's set them up like this. So we'll keep the scale even on both sides. All right. So a simple parabola, like so. That's the graph of y equals x squared. Now, what if we want to mimic the motion of some, orbiting object or thrown object? Then, of course, we can't use this parabola. We need to modify it somehow. So let's take a look at this example down here, this function. 4 minus 1/2 x plus 1 all squared. What does that graph look like? Well, fortunately, we can see that essentially it's the graph of y equals x squared, but with some tweaks, with some modifications. And if we remember what those are, there's a few, we'll review these in a second, but let's see how much you remember on your own. Think about what the 4 does, the -1/2 multiplying, and the x plus 1 on the inside. I like to work from the inside out, and remembering that shifts or addition and subtraction inside the function, they act in the opposite way to what you might expect. So here we're going to remember that this is going to be, you'd think with plus 1 it might move right, it'll be a left shift by 1. What does the half do? It's a vertical scaling. In this case here, it's going to shrink the graph vertically by a factor of 2. This negative sign corresponds to a flip vertically. Everything that was positive coming out of this squaring function is now going to be negative, so things that were positive are now going to move to the other side of the y-axis. And then we've got the 4, which is a vertical shift up by 4. Okay. So how can we work our way through this? Well, the key things for sketching a simple graph like a parabola is to look at where maybe the vertex went. So we know the vertex would be shifted by 1 to the left. So 1 to the left. It'll be shifted up by 4. So we expect to see a vertex at -1, 4. Just as a side check, it never hurts to do this, especially if you're a little rusty on transformations. Let's plug in x equals -1 into our graph here. We're going to have 4 minus 1/2 minus 1 plus 1 squared. Well, that's 0. And so we're going to end up with the coordinate 4. So absolutely, -1, 4 is one of the points on our graph. All right, so trusting that vertex move was correct, and then we have some faith around the other points in this transformation and the other effects of this transformation, we're going to be able to sketch out not the regular parabola. It's not the same parabola. We said it would be shifted, compressed vertically by a factor of 1/2. So instead of going down by 1 each time on the first step, it's going to go down by 1/2. On the next interval, it's only going to go down by 2 instead of by 4. And then 3 would be 9. It'll go down by 4.5. 1, 2, 3, 4.5. And that'll give us a good picture of our new function here. So still a parabola, very definitely a parabola, but transformed rather substantially from what we started with. So take a look at that and make sure the pieces are falling in together with what you remember from your pre-calculus study of functions. Just as a brief reminder, let's take a look at the 4 common types of transformations and how they're represented both mathematically and the kind of transformation we would see in the graph as a result. So one of the transformations, of course, is a horizontal shift, and that would be something you'd see if you started off with the graph of f of x, and then turned it into f of x plus a or f of x minus a. And so one example might be sine of x, and you might go, say, sine of x plus pi over 4. Remember, in calculus we always use radians and not degrees as much as possible, certainly when we're doing derivatives, as we'll see later, but in general it's good practice to stay with radians rather than degrees. In this case here, that would give us a left shift by pi over 4. Let's just do a quick sketch of what that might look like. Remembering your graph of sine of x is the one that starts at 0 and then oscillates from there. It takes a full 1 pi to get one loop and a full 2 pi to complete a complete cycle, and so on. If we were to graph that as y equals sine of x, then the graph of sine of x plus pi over 4, here's pi over 4 here, it would be shifted to there, and we'd see two sidestepped functions like so. There we are. Y equals sine of x plus pi over 4. There we go. So that's a simple horizontal shift, and again, the only trick is remembering that transitions or transformations inside might seem counterintuitive. The plus is going to make a left shift, a negative would make a right shift. Another transformation that we'll see is a horizontal scaling. So if we have a function of x and we know what it looks like, what we might do is multiply inside, and that'll create a horizontal shift in the graph. And so that'd be a horizontal compression if that c value is larger than 1. So if we multiply by something bigger than 1, that makes things happen faster when x changes, and that compresses the graph. And a horizontal expansion if c is between 0 and 1, or actually if c is less than, the absolute value of c is less than 1. We also have the possibility of flipping, a horizontal flip if c is negative. So the other two common shifts and transformations are a vertical shift, and that would occur if we had f of x being replaced by f of x. Notice the location plus some value outside the function, and that's the key ingredient here, that's outside f. And what might that look like if we had sine of x plus 2, for example? Then we do the sine of x calculation, then every value that comes out of that we add 2 to it. Then if we sketch the graph of sine of x, it goes up to 1 usually. Well, it always goes up to 1, but when we add plus 2 to it, it's going to take all of these coordinates and shift them up by 2. Let's just clean this up so it actually goes through the origin like it should. There we go. So if we add 2 to each y value, instead of sine of 0 being 0, we're going to have sine of 0 plus 2, and we're going to have a graph that goes like this. And it's going to go down to 0 here. Oh, sorry, no it's not. It's going to go down to 1. There we go. That would be y equals sine of x plus 2. And y equals sine of x. The intercepts now being 2, and this value here being 1, because when the graph ordinarily goes down to -1, we'd have -1 plus 2, move it up by 2, and we get the green graph line there. Last but not least, we might encounter, and we certainly will encounter, vertical scalings. That's when we have a function that gets replaced by some constant, but now again outside the function itself, and classic for this would be sine of x being replaced by, say, 3 sine of x. We have our graph, we have sine of x here, which ordinarily goes up to height 1. And now, well, when x is 1, or when sine of x is 1, we're actually going to get 3 times that in the y value. So we can landmark it here and here. There we go. Notice that it's a stretch away from the y-axis, sorry, yes, from the x-axis, because everything that was positive gets more positive. Everything that's 0, well, if sine of x is 0, multiplying it by 3 doesn't change anything. The y value would stay at 0. But then everything negative gets magnified as well. So everything is spread outwards from the x-axis. All the vertical things are stretched away from the x-axis. So that would be y equals sine of x with a 3 out front. And the blue line again is y equals sine of x. Those 4 shifting and scaling properties or transformations are the ones we're going to use throughout this course. So if they're less familiar, I'd recommend going back to the textbook and simply reviewing them for your own benefit.